it's a pleasure to have our three speakers that will give us a series of lectures on recent developments about cluster algebras and Legendrian links. And the first talk is going to be given by Roger, and he'll talk about Lagrangian fillings of Legendrian links. Go ahead.
Thanks, Mohammed. Thanks to the organizers. So thanks everybody for attending. Yeah, as Mohammed said, the goal of today is to highlight some of the recent developments in the study of Legendrian links and Lagrangian fillings, in particular as they relate to cluster algebras. And this first talk is meant to be introductory, introducing new ideas, but mostly introductory on what's to come as well. At any point, if you want to interrupt, please do so, ask any questions. And if I'm going too slow or too fast, feel free to share how you feel about it, and we can adjust accordingly. So let me start by just stating that in contact topology, the study of Legendrian submanifolds has been very useful. It is very useful in one dimension. So the Legendrian one-dimensional, three-dimensional contact topology, we tend to think of Legendrians as being these fronts, which are some sort of knot diagram, but now for Legendrian knots, Legendrian links. And I want to point out something that doesn't happen every day, which is there was a beautiful movie of fronts in the New York Times a few months ago when a volcano in Tonga exploded, and people did track the wave that created throughout the Earth. And it was a fantastic Legendrian isotopy that lasted for 72 hours, longer than the ones I usually work with. But yeah, you never know where contact topology will pop up. General comment for people who might not be familiar with Legendrians, you can use Legendrian submanifolds and in general Lagrangian submanifolds, filling them to prove non-vanishing of symplectic homology or to compute some invariants via the surgery formula. You can use convex surfaces and Legendrians to classify contact structures. They are in general useful, even if that's not your prime starting point of interest. I also just think they're very beautiful. And if you think about lights and caustics, they do appear every day, everywhere. So I just like to study them on their own right. So now we're going to delve directly into sort of these developments. And what I want to start with is the geometric problem that motivated this. And the geometric problem is the study of Lagrangian fillings of Legendrian links. And I'm going to be restricted to the following setup. We're going to study a Legendrian link in the unit cotangent bundle of R2. And it's fine to think about it as being inside a larger Darboux ball. So if you want this to be R3, that's fine by me. If you want this to be S3, that's also fine by me. So this is a very local problem. It's a useful problem to understand because if you're studying more complicated symplectic manifold, Weinstein manifolds, things like that, you certainly always have those Darboux balls. And so whatever behavior is happening in that Darboux ball probably will tell you about at least how complicated the symplectic manifold will be overall. Now, the study of Lagrangian surfaces in this particular setting is about fixing a symplectic filling. So this is my symplectic filling in here, is the standard Darboux symplectic ball. And in the boundary of that, I have my lambda. I either have it in a Darboux ball in R3, or I just satellite it along the unknot if you really thought about lambdas being in J1 of S1. And the problem that we're faced with is try to understand existence, uniqueness, properties of Lagrangian surfaces L inside of the four-ball, which are embedded and exact. Now, embeddedness can oftentimes be relaxed, and a lot of the things that I'm saying will also be useful for immersed exact Lagrangian fillings. Exactness is a pretty important property for the description that I'm going to give, because we're going to have to use Legendrian lifts of these surfaces. But there should be a theory without the exact word in there, and that has not yet been developed. But you know, there's to hope. So the question is, classify embedded exact Lagrangian surfaces in the four-ball, standard D4, which have this fixed boundary condition lambda, and the equivalence is exactly compactly supported Hamiltonian isotopies. All right, so yeah, there's I think Mohammed, you posted the slides in the chat. Is that what happened?
No, not yet. I will do it in a minute.
I put them there.
Okay, thanks, Nate. Right. Okay, so some comments on exact Lagrangian fillings of lambda. They're somewhat studied. We have some understanding of it, but there's a lot to be said about them that remains. The first comment is Lagrangian fillings might or might not exist. If you're given lambda, it might have a Lagrangian filling, it might not. Now, this actually does not depend on the smooth type, in the sense that like the same smooth type might have different Legendrian representatives, some with fillings, some with none. So this is a subtle thing that has to do with contact topology. A good thing is that when there exists an embedded exact Lagrangian filling, they actually minimize the genus among all the surfaces in the four-ball. So that maybe makes you think that, in contrast to the smooth topological problem of understanding all possible smooth surfaces in the four-ball bounding a given knot, this symplectic problem is slightly more doable. And indeed, there's a nice conjecture that I will discuss maybe in the next talk, stating that for lambdas that come from a positive braid, we now have a conjectural classification of what those Lagrangian fillings should look like. Note that if you were a 4-dimensional or 3.5-dimensional smooth topologies, studying surfaces in the four-ball bounding knots, the problem for the unknot is already unknown. So for instance, if you ask the question, how many disks, even if you ask for ribbon disks, are bounded by the unknot, it's not known to be, say, unique. So we don't even know whether there's a unique ribbon disk bound in the unknot smoothly. Yet in the Lagrangian setting, like we know the Lagrangian disk is unique. So it makes sense that maybe those classifications are possible in symplectic topology, even if the smooth setting is more wild. The last comment here is those Lagrangian surfaces, I mean, I do like them as geometric objects. I just tend to think of them as they are for what they are. But if your heart tells you that you really want to be thinking about categories or some other algebraic framework, then those Lagrangian surfaces will give actually nice objects in those categories. So you take the Rav-Fukaya category, stopped at lambda, those Lagrangian surfaces are objects there. In terms of shift categories, same thing. Mirror symmetry does indicate that the moduli of Lagrangians has something to say about the mirror. So in that setting, those Lagrangian surfaces can try to be used that way. Not what I do, but they can be useful that way. All right. So this is a geometric problem. I give you lambda. What are the Hamiltonian isotopy classes of L? In general, suppose maybe it exists. Can you build other ones? So on and so forth. Okay, so let's answer that first question. So suppose I've actually given you this lambda in here, and I've actually given you one L. So I actually know this L exists. Is there a way to modify that L in a way that I obtain some other embedded exact Lagrangian filling, which is potentially not Hamiltonian isotopic? So now I'm discussing geometric constructions that will build candidates that might have different Hamiltonian isotopy classes. There is, of course, later the task of distinguishing them, which we will address. But for now, what I'm going to tell you is that if you have a Lagrangian filling L, as it's given here, and you happen to have found a embedded exact, well, it's always exact, sorry, an embedded Lagrangian disk like this orange guy here on the complement of L. So this guy is a disk, D2, which is Lagrangian, and it lives on the complement of L. And this guy is Lagrangian. So suppose you found that. You look at L, and by whatever means you found that disk, then there is a nice operation called Lagrangian disk surgery, really building on a local model developed by Leonid Polterovich, also known as Polterovich surgery, that does the following for you. It allows you to locally in this ball shrink that disk to a point and then grow some other disk in some specific way. This is a local model construction. You use that local model in there. And now the purple disk is not exactly the orange disk. And the resulting Lagrangian, in fact, will not, in many cases, be Hamiltonian isotopic. So this guy will typically not be the same as L, as an embedded exact Lagrangian. It will be Lagrangian isotopic, not compactly subordinate Hamiltonian isotopic. So this general construction does preserve the smooth class of L. It does not typically preserve the Hamiltonian one. And the Lagrangian disks, the orange and the purple, are Lagrangian themselves. So if you want to think about this picture in one dimension, it just looks like that. And this is essentially like the way Polterovich does it. It's some spinning around this construction. So this would be the Lagrangian, and this would be the disk in here that gets shrink to a point, and then it continues. Note that this Lagrangian in the middle is immersed, and in a sense knows about both, the one on the right and the one on the left. Okay, so knowing that we have this construction, it now seems natural to just consider the geometric problem of, can I build Lagrangian fillings, as we were considering before? And also, can I build as many disks like this guy on the complement of that L, such that the boundary of those disks are in L? And that's the next geometric problem that I want to address. So it's the same as the previous one, study L, but now study L with these disks on the complement. So here's a precise definition that works well for almost everything I will say, as long as the Legendrian is associated to a braid beta, which is of the form beta delta square. I will make a comment on what happens in general. So by definition, an L-compressible system for L is just this collection of Lagrangian disks properly embedded in its complement, such that you can take the closure of the disk and then look at the curve that they give in L. And you want that to be maximal in the sense that, for instance, they generate H1. So this maximal in here is generate H1. All that this is trying to do is to say, find as many disks as possible as you can on the complement of L. Don't do something silly, like take the same disk twice. And so you want this linearly independent connection that generates now. Now, the quick technical comment that I have to make here, and it will be mostly swept under the rug, but it is very interesting, is this word embedded in here. Typically, you can prove that you cannot actually find such collections always, but it's possible if you ask for some of these disks to be immersed. So if you allow yourself for some of these disks then to be immersed, then you do gain a lot. And in general, for the cluster algebra business, the embedded disks are going to give you mutable vertices in the quiver. They're going to give you mutable variables. The immersed disks are going to give you frozen vertices. They're going to give you frozen variables, meaning non-vanishing functions all over the space. So that's the geometric definition. I now want to ask, if I give you a lambda, does there exist an L with an L compressible system for it, and maybe as maximal as possible? Okay, so here's a first start. A nice class of Legendrians is, for instance, that of algebraic links, in the sense that you take an isolated singularity that has a link, and that link, if you think classically, it's typically thought of as transverse, but you can ask about all Legendrians that have that link, transverse link, as their transverse push-off, their positive transverse push-off, and then ask that those Legendrians must be max TB. Very beautiful theorem following work of Nair and Lafontaine, is that actually that Legendrian link is unique. So given an isolated singularity, which you would typically think of gives you a transverse link, actually also gives you a unique Legendrian max TB representative for that smooth type. And that's a good place to start. Now I have a Legendrian for every singularity. And now you can ask, can I build a Lagrangian filling? Can I build an L compressible system? So there's a construction. This is in a paper that I wrote for the Viterbo 60 anniversary volume that explains how, given a real morphification, you can actually build an embedded exact Lagrangian filling associated to that real morphification, and it comes with a natural maximal L compressible system. What I wrote here in red is accurate. L is quote unquote a Lagrangian Miller fiber. It is smoothly the Miller fiber, and it just happens to be Lagrangian. And Di are the vanishing thimbles. The fact that the vanishing thimbles are Lagrangian should surprise nobody. The fact that the Miller fiber can be made Lagrangian, it's slightly more work. But that is a construction that exists. So that's a good source of examples. For instance, a trefoil knot is the link of the singularity given by x squared plus y cube, the A2 singularity, and it has a real morphification for which you can see the Lagrangian Miller fiber being exactly this once punctured torus, and then you see this disk as one of the vanishing thimbles, and the other disk as the other vanishing thimble in here. So I can explain that in more detail if you're interested, but what you see on the left is a front for the trefoil. What you see on the right is a Lagrangian filling with the L compressible system. Okay, so here's a class of examples. Now I'm going to sort of vastly generalize this. I'm going to explain how to build Lagrangian fillings in L compressible systems for a much larger class of Legendrians. For instance, for the Chekhanov pair, so if you take the max-dB Legendrian representatives of M52, the mirror of the 5-2 knot, there's two of them. None of them are of this sort, but you can show that one of them is actually the closure of a positive braid, which is exactly what I'm going to do in a moment. Okay, so to conclude this first part of the talk, I just want to comment on a couple of standard things that this machine or these sort of geometric objects allow you to do. And then I want to point out what's new, what kind of new things we can prove that maybe are not so standard. So the first thing is, it's perfectly fine, and I almost would encourage you to think of L compressible systems as actually being some set of disks that you can join with L. So you can consider the geometric union of L and the disks in your L compressible system, and that creates a Lagrangian CW complex. It's arboreal, if you know what that means. And what you have obtained now is this nice Lagrangian CW complex inside of the four-ball. And in fact, this is a Lagrangian skeleton in the sense that there exists a Liouville flow in the choice of Liouville form and a Porous harmonic function, such that the model is Weinstein, that retracts everything to exactly that Lagrangian skeleton. You know, think about this picture that you have in front of you, or think about the trefoil that we just drew before. Like, the once punctured torus is not a Lagrangian skeleton of the four-ball. The four-ball has no topology. It can possibly retract to the Lagrangian filling of the trefoil. But if I add enough disks, those are going to kill the topology for me. And in general, you can think of these problems of L compressible systems more generally as trying to understand relative Lagrangian skeleta for the Weinstein pair given by the four-ball, and then lambda, if you're really picky, a ribbon of lambda. So it's a Weinstein hypersurface on the boundary. And that's kind of a geometric Landau-Ginzburg sort of picture. The second comment for that is when you take the Rapp-Fukaya category for this pair, meaning the Rapp-Fukaya category of the four-ball with the stop at lambda, these guys actually give you a very natural set of generators. So one thing you can naturally do geometrically is, in this Lagrangian disk, take the cotangent fiber. In this Lagrangian disk, take the cotangent fiber. In this Lagrangian disk, take the cotangent fiber. This is a set of objects that belongs to that category, and I call this like D star. It's kind of like the cotangent of the disks. And then furthermore, you can also take kind of the cotangent fiber of L. You will typically take it here as a linking disk for lambda. That is a set of objects in the Rapp-Fukaya category, partially stop at lambda. You can take the direct sum. You can compute endomorphisms. Work of Ganatra, Pardon, and Shende, I think paper number 2, show that these objects actually generate the Fukaya category. And interesting to me, and I will comment that later in the second talk, there are typically many L compressible systems. How do they change? How do these generators change under a Lagrangian surgery? All of those questions to me are interesting, and I don't think they're understood at all. So it's like, what is that endomorphism algebra? Even in particular examples, I don't think this has been computed. So here you find yourself in this sort of dissonance where on the one hand, you have all these structural results where you know the Fukaya category is generated by some objects here and there, but then you have what for me is sort of what I encounter, which is, okay, is this actual knot, this actual compressible system? How do you compute that endomorphism? Give me a presentation of that DGA, give me something explicit. And I think that explicit part is still to be worked out in more detail. Okay, so this sort of standard use, I think any symplectic topologist should probably understand what's happening here. Like, what's new about it is that these L-compressible systems can be used to construct what will be called a cluster algebra on some space. That space will actually be a space that is incarnating, is trying to be the moduli of Lagrangian fillings for that lambda. So I'll explain exactly the categories and algebraic varieties involved in this construction later, so I'll keep now focused on the geometry, but the punchline is these L-compressible systems, these Lagrangian fillings with this kind of complement, will actually allow you to say, oh, this category has this property, this algebraic variety actually has these special properties. And the way it goes, if you know what a cluster algebra is that the L-compressible system will give you a quiver given by the intersection of the boundaries of the disks. And what's really sort of the surprising thing is that each disk will give you a regular function on those modelized spaces. And then you can ask how these change under Lagrangian surgery. And being cluster in part is about saying that the changes of these regular functions are given by some kind of universal formulas known as cluster mutations. All right, that kind of concludes the sort of the introduction on what's happening, the Lagrangian fillings and L-compressible systems. Now, next in the talk, I'm going to discuss the geometry. How do you build these L-compressible systems? And afterwards, I'm going to discuss exactly what this M lambda beta is, what this model I is, and how do we go about constructing these functions. So I'll stop for a second. Are there any questions at this point? All right, maybe I'll move on, but feel free to interrupt at any point. So I stick with the geometry now. I stick with my lambda. Now I want to build, given a lambda, L's and L-compressible systems for it, for those Lagrangian filling L's. Now, the first thing that happened is that typically lambda might not have a Lagrangian filling, and even if it does have a Lagrangian filling, it might not have an L-compressible system. So the first thing I'll do is I'll restrict myself to a class of lambdas which are associated to positive braids. There are several reasons to do so at this stage. I'll comment on them in the next talk. Mainly, we, for instance, cannot even name what it means to be a clustered algebra for the moduli that appear in those general settings. But for a braid of the type lambda beta, we can actually do everything very explicitly, and those moduli spaces will actually be affine, smooth algebraic varieties. So things are sort of down to earth and can be named and compared with the classical theory of cluster algebras. All right, so how do we go about building these Legendrians lambda beta? So you give a positive braid, you draw it here. I've drawn here some random positive braid. So you draw a positive braid, and then you take the -1 closure of that, which just means in the front, you're just going to do something like take this kind of thing. Geometrically, what this means is you take the satellite along the standard Legendrian unknot in R3. So you consider these Legendrians naturally associated to a positive braid beta, and now you try to build a Lagrangian filling for them and L-compressible systems for them. Now, weaves are exactly the kind of tool that allow you to address that problem. Weaves built for you Lagrangian fillings, and they built for you L-compressible systems for that class of Legendrians. Now, what is a weave? Well, it depends kind of who you ask, but a very combinatorial mindset on this is a weave is some picture in the plane. This is the kind of picture which has a bunch of colors in it, and then it has things like trivalent vertices and hexavalent vertices. And there's some rules about how these lines can interact with each other, but if you really are into kind of diagrammatics and combinatorics, this has the advantage of stripping the symplectic topology and translating everything into some combinatorial rules that then you can use to manipulate these Lagrangian fillings and construct these L-compressible systems. Now,
sorry, Roger, I also see some 4-valent vertices in there.
That's correct. So there are 4-valent, and they are allowed as long as the transposition associated to this. So this transposition is disjoint from this one. So they're IJ apart. So they don't talk to each other. So that would be the 4-valents is going to correspond to something like two crossings like that are allowed to go this way and that way.
Thanks.
Yeah, thanks. Yeah, good point. So let me just say for now, how do you read the braid? Just forget about the Lagrangian filling and the compressible system for now. How do you read the braid? And the way you read the braid is cyclically around the boundary. So start at any point here, and then you start going, and then each color is going to give you an arting generator. So for instance, the arting generator for the green, it's going to be sigma 1. For the blue is going to be sigma 2, and for the red is going to be sigma 3. So that braid is going to be sigma 3, and then sigma 1, and sigma 2, 1, 2, 3, and you keep going around the boundary, and you can read the braid this way. Different starting points will just give you cyclically equivalent braids, which give you Legendrian isotopic lambdas, so nothing changes. Everything is independent where you start with. So the boundary of this kind of diagram gives you the positive braids, gives you the Legendrian. How you fill that diagram, that's about the Lagrangian filling, that's about the compressible system. So let me be systematic about how you can build some of those diagrams. The geometric idea is as follows, we were discussing exact Lagrangian surfaces. These are Lagrangian surfaces L2, like two-dimensional Lagrangian surfaces in a four-dimensional space. For me, hard to draw, hard to visualize. Nevertheless, because they're exact, they admit a Legendrian lift into contact R5. So now you're discussing Legendrian surfaces in R5. This might seem slightly counterintuitive. If you couldn't draw surfaces in 4D, how can you draw surfaces in 5D? But the advantage is that Legendrian fronts are exactly of dimension n+1 if the contact manifold is dimension 2n+1. Whereas Lagrangians would be n inside of 2n, and the Lagrangian projection is not going to help you in that manner. So the punchline is lift this to a Legendrian surface, L twiddle still two-dimensional in R4, but then use the fact that the Legendrian projection of this L twiddle now lives in R3. So what you've gained is that you've been able to go from 4 down to 3. The trickiness, obviously you got to pay something. This 4 to 3, the payoff is this was a nicely smoothly embedded surface. This is no longer smoothly embedded. This has singularities. But now you can just say, well, I'm fine. I'm going to pay for this. So I'm going to now study spatial fronts, no longer smooth surfaces, but singular surfaces. But maybe I can understand those. And indeed, I can. Well, Arnold could, and now I can. And we understand them as a community. And so we can maybe try and draw that. So how do we think about it sort of in practice? Well, one way to build Lagrangian cobordisms and ultimately Lagrangian fillings is via Legendrian isotopies and also by what's called a Lagrangian surgery. So attaching a 1 handle or a 2 handle or 0 handle at the Lagrangian level. And among all those choices, there's 2 of them that I want to focus on. The first one is the Rademeister 3 move. And the second one is this thing called the D4 minus cobordism. I'm throwing away the Rademeister 1 and Rademeister 2. I'm throwing away more complicated cobordisms. And I claim that actually for this class of Legendrians, these 2 guys will do the job. So how does this go? Let's start by the R3 move. Well, if I have a Legendrian lambda and I find myself with this picture in the front, I can perform a Rademeister 3 move and go to this picture. All right. What does this do at the geometric level? I could take the trace of that isotopy, and that would give me a Lagrangian concordance. It's just a cylinder from the lambda on bottom, lambda minus, to the lambda on top, lambda plus. So that is this Lagrangian concordance in there. All right. So why aren't we happy with that? Well, how do I draw the Lagrangian concordance? Well, what you do is you take that embedded exact Lagrangian cobordism, which is a cylinder in this case, cylinder over lambda minus, and then you lift it, as we said before, to R5, and then you project it to the front projection. So how does that look like? Well, the first statement is, how does it look at the boundary? So if you think about what the front would look like once you've lifted and projected, all you would see from above, so this is a picture of what happens in R3 when you look from above. So now you project down to the coordinates x1, x2 in this R3. All that's happening is that you're reading this positive braid by keeping track of the crossings. So red translates into red, blue translates into blue, red translates into red. So for now on, I'm going to read positive braids. I'm going to read this kind of Legendrian lambda beta just by saying, here's the crossings. It's a sigma 2, it's a sigma 1, it's a sigma 2. It's a very natural thing to do. The way you read a braid is a linear thing. It's a one-dimensional information. Why would I draw it in the plane? So now these braids are encoded in 1D, which now has the advantage that the cobordism can be encoded in 2D. And what you find here is an A1 cube singularity for this R3 cobordism. And what's happening is this crossing gets translated to the other side here. So this crossing over here, this crossing on the upper left, as you do the Rademeister 3, goes down, goes down, goes down, and becomes this guy. So this translation is exactly this translation. So at the end of the day, the conclusion is if I draw the Legendrian lift and then I project for that R1, R3 concordance, I end up having this A1 cube singularity. And if I keep track of the A1 square singularities, the crossings, they look exactly like this hexavalent vertex. Now, the same story works for whichever operation you want to do. And in particular, there is the covariism, which is called D4 minus covariism, that goes from these two crossings to this one crossing. I can break it down in steps if you want, but you can also just take it as a black box. This is lambda minus in here. This is lambda plus in here. And that covariism is a subtle covariism. It has one Morse point of index 1. And what happens when I Legendrian lift it and I project down to R3 and then I look at it from above? Well, these 2 points in here, the 2 points, the two crossings that I had in here, this guy and this guy are just these two guys. This guy above is here. And what you see above is exactly this trivalent vertex, where again, what I'm keeping track of are the A1 square singularities, the crossings of two sheets in the spatial front. And there's this funny singularity in the middle called the D4 minus, which is not generic, but it's fine. You can use it, it works, it gives you this covariism. So claim with these R3 concordances and these D4 minus covariisms, I can build Lagrangian fillings, I can build L-compressible systems for all this lambda beta. A quick comment is you're also allowed to do a cyclic shift, as I mentioned before. And for that kind of cyclic shift, you just like move the weave around, so sort of cyclically, you just move the whole picture around. I won't discuss cyclic shifts much, but they're key in order to perform some of the operations, in particular to access infinitely many seeds. So keep in mind the R3 move, the D4 minus covariism, and maybe keep in mind that you can do cyclic shifts. Okay, so now let's explain how to produce embedded exact Lagrangian fillings of these kind of lambdas, lambda beta, via these two moves, the R3 moves and the D4 minus. And now everything is pictures because I'm drawing from the front and I'm looking from above, I've projected to the plane, keeping track of the A1 square singularities is enough. Well, and which sheets are above, which is what the permutation does for you, is enough in order to describe these exact Lagrangian fillings. So here's the real sort of down-to-earth problem. I gave you a beta. I don't know. I came out with some beta, like 1, 2, 1, 1, 1, 2, 1, 1, 2, 2, 1, and then delta. So this is the half twist in general. You can check exactly what the smooth type of the -1 closure of this is. This is the 3-4 torus knot, and it's always a max TV representative. So in fact, this is unique. And now you're starting with the word beta on top. This is beta. Now, how do I build this Lagrangian filling? There's a kind of weaves, we call these Demazur weaves, and Jose will elaborate on that more, that what they tell you to do, and they work well because if you follow the instructions, is that you start with beta, and then you end up here at the bottom with the Demazur product of beta, which in this case is just the half twist. So the name of the game is you start with this word in here on the top, and then you will start doing operations that either do sigma I square goes to sigma I. This is very reminiscent of the Nil-Hecke move in Hecke algebras, or you do Rademacher's threes in whichever direction. So fill this diagram with pictures, these three types of pictures, D4 minus, and then these two kinds of R3 moves, such that you end up at the bottom with this. Okay, what can you do? So for instance, here's the solution. This is beta on the top. This is beta here. This is delta on the bottom. And the first thing you do here, as you scan down, you first do this. Two guys get joined into one, then these two guys get joined into one, this also get joined into one, then you do the Rademacher 3, then these two get joined into one, these two get joined into one, these two get joined into one, another Rademacher 3, and you keep going down, 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 down. And the claim is you can always do this. You can always go from beta to the Demazur product of beta by these operations. So sigma I squared goes to sigma I and Rademacher 3 moves. And furthermore, and that's a non-trivial geometric statement, but it can be proven, not too hard either, is that this front, when you think of this diagram for what it is, which is a front seen from above, if I take now this Legendrian surface and I project it down to R4, is actually embedded. So it's exact by construction, because I did it through a Legendrian lift, but it could be immersed. A priori, there could be rep chords for this Legendrian surface. And the claim is, if you know how to draw the weaves well, meaning you follow the instructions I've given for Demazur weaves or that I've given for some other types of weaves, you're guaranteed that the endpoint is an embedded exact Lagrangian filling. Namely, there are no rep chords in that. So that is a geometric statement, but as I said, it can be verified. So that is a Lagrangian filling. That is a Lagrangian filling for the MaxTB T34. And you're saying, wait, there's a lot of choices here. Why did you start like doing these two guys and not like, I don't know, why not these two guys here first? And indeed, that's entirely correct. Typically, there's many solutions to these. So for instance, these two solutions differ exactly by what I said. In here, these two guys are pinched first, they come together, and then these two guys come first. Here it's reversed. These two guys come first, these two guys come later. All right, so now you've built two a priori different Lagrangian fillings for this knot. Can you tell them apart? How do they differ geometrically from each other? And that's what weaves does. The paper that sets the foundation of weaves, which is a work with Eric Zaslow, it's exactly doing that for you. It's explaining all these diagrams, what do they mean symplectically, how they're related to each other, so on and so forth. As I said before, if you allow cyclic moves, you can actually build infinitely many solutions of that sort. So that gets you going, thinking, oh, maybe there's infinitely many Lagrangian fillings. Because a priori, I seem to be able to build very different weaves in that manner. And indeed, that is what happens in the end. So many solutions, as I said, always exist a solution. And in fact, many solutions typically. So now we move on to the main structural theorem. So now you just want to have a black box that tells you, how do I use this weave calculus? Now that I understand what it is, how do I use it diagrammatically to operate? So, okay, you're given the braid beta, you're giving this Demazur weave that goes from beta to the Demazur product, delta. And then the first claim is, if you've built it that way, this is an exact Lagrangian filling. Oh, I should have added embedded. Apologies for that. So this is an embedded Lagrangian filling of your Legendrian. So you're pretty happy. You've done the first thing. And now you start asking very natural questions. Suppose I've given you two weaves. Like, how do I know whether they're the same Lagrangian filling or not? So first statement, this series of combinatorial moves actually preserve the Hamiltonian isotopy class of the Lagrangian filling associated to the weave. So if you came to me and you saw a piece of the weave like that, and you said, no, I'm going to exchange it by these are all moves relative to the boundary. Well, that's fine. That is a different weave diagrammatically, but the Hamiltonian isotopy class is exactly the same. Not just that, but as we will see in a second, these are going to be all the kind of moves that we need with the addition of the Lagrangian dissurgery. So for now, let's just say these moves are Hamiltonian isotopies. So that's a good thing to do. You can start manipulating that manner. The second comment is, all right, you explained that you want to build Lagrangian fillings, but you insisted on this thing called L-compressible systems that seem to be very important to the Lagrangian dissurgeries, to compute stuff. Indeed, we've solved that problem for you. I'm going to explain that in an example explicitly in about 3 minutes, but there is a way to name combinatorially some kind of edges in the weave called white trees. And once you name those edges, you automatically are given a curve in L. So they give embedded curves in the Lagrangian filling L, and you're guaranteed that those curves bound embedded Lagrangian fillings in the complement. Therefore, you can do Lagrangian dissurgery. Therefore, you can try to build L-compressible systems that way. So that's, again, something that we started geometrically asking, can we build those L-compressible systems? Weaves do that for you. They build them. All right. Comment number 3. Okay, if you look at the two solutions that I mentioned before, they differed by a move that looked like that, this white-hand move on trivalent graphs. Is this a weave equivalence? Have I preserved the Hamiltonian isotopy class of L? Typically, no. You prove that this move on weaves is exactly Lagrangian dissurgery. And it can be done locally, as exactly in this picture, but there's some more complicated mutations, which are really just bootstrapped from this one. So the key move is this one. But a priori, a mutation can look as something more complicated. But if you apply weaves equivalence, just think about this as being the key move. And all the other mutations are sort of equivalences plus that key move. All right, you had your equivalences. Now you have this other white-head move on trivalent graphs that you can apply. That gives Lagrangian dissurgeries. Dictionary is going nicely. And now you ask the question, well, what about if I have two weaves for the same lambda, right? I have two Lagrangian fillings, maybe both of them are given by incompressible systems in addition. One is a weave, the other is also a weave. Are they connected in any way by just Hamiltonian isotopies and Lagrangian dissurgeries? And this is one of the key things in this calculus, which is yes. In fact, if I build two dimerized weaves for the same beta, then you can go from one to the other via equivalences, these combinatorial equivalences, and mutations, which in symplectic topology translates, you can do a series of Hamiltonian isotopies, very explicit ones, and Lagrangian dissurgery, and that's going to allow you to go from any Lagrangian filling built in that manner to any other Lagrangian filling built in that manner. Again, just to point out, it's a completely open problem, hard in my brain, to classify all possible Lagrangian fillings of a given lambda, or to even say whether two Lagrangian fillings are, related by some sequence of nice moves. Obviously, you have arboreal skeleton, you have one parametric versions of that. But if you think about those kind of skeleton, they will typically use what I call fins. So the skeleton is not going to be closed. You're going to have to add some pieces, and the thing no longer looks like a Lagrangian filling plus disks. So you have that general statement. That's an H-principle statement. But what I'm claiming is for this class of Legendrians, for this class of fillings, you can do much, much better. You can just do displicit equivalences and Lagrangian dissurgery. You never need to grow fins. You never need to do anything funny. And it's done sort of proven combinatorially. Okay, so let's just finish this part with an example. Let's take the same example as before, the 3/4 torus knot, the max Tibet representative. And now, as I said before, this is one solution, that's the other solution. The only difference is exactly here. Well, we just said that in the theorem, the structural theorem, the framework for weave calculus says these two guys differ exactly by one Lagrangian dissurgery. Okay, now let's dive deep down into the real content of all this calculus, which is the construction of L-compressible systems. So how do I find L-compressible systems? Well, this is what white trees are. So I'm using this example as a slide to also define white trees. So white trees are a collection of edges inside of the weave with the following property. So it's homomorphic to a tree. It's going to have some tree-like structure. Maybe I'll do it like this. And it must have the following properties. The ends of the tree must always be trivalent vertices. So these guys, these leaves, must always be in trivalent vertices. And then inside of it, the only thing that it's allowed to do is in an hexavalent vertex. So if you're in an hexavalent vertex like that, it can do two things. The tree can do two things. So I'm going to draw the tree in gray. The tree can go past from anywhere in here across, or the other two. So it could also do these, or it could also do that. It can just go through the hexavalent, or it could branch out. So for instance, two could arrive and then one could come out. So you could choose either the blue guys or the red guys. So what you see here in the tree are not trivalent vertices in the weaves. They're actually hexavalent vertices in the weave. So again, a combinatorial description that now allows you to solve a symplectic problem. And I start with a very simple white tree, Y, like this gamma one. Well, that's a line. That's indeed a tree as a graph. And it goes from this trivalent vertex to this trivalent vertex. So that's one embedded curve in your Lagrangian filling that bounds a Lagrangian disk. Okay, let's go for a funkier disk. So a funkier disk is this one. It's the gamma 2 one. It starts here at a trivalent. And then in the hexavalent vertex, it branches with the blues. It ends at this trivalent. It continues like that, and it ends in here. That's another embedded curve. It's actually having intersection 1 with gamma 1. You can compute intersections by intersecting these white trees combinatorially. Therefore, it's linearly independent with the previous one. And now you keep on going. So for instance, now you take gamma 3. That's a very easy one from trivalent to trivalent. Gamma 4 is very similar to gamma 2. So it starts as trivalent and then it branches in two ways. Gamma 5 is also easy. So what about gamma 6? Gamma 6 is slightly interesting with respect to the others because it starts as a trivalent and then it goes through the hexavalent and it continues to go until it matches here. So gamma 6 is an example of somebody that goes through an hexavalent without branching into two more leaves. So now I've depicted 6 curves for you. These are 6 curves in this Lagrangian filling, in the Lagrangian filling L associated to this weave, what is the genus of L? Well, the genus of this is just the genus of the 3, 4 knot. So that's going to be 3 minus 1, 4 minus 1 divided by 2. So that genus 3. Therefore, B1 is exactly 6. And you can check by hand that these are all linearly independent. So checked. Now you've built an compressible system, a maximal compressible system. All these are embedded curves, all these bound Lagrangian disks on the complement. So that's going to translate into the fact that this teeth is going to have all mutable vertices, 6 mutable vertices to start with. All right, so that is an explanation of how to sort of diagrammatically build that, and the framework for weaves tells you this is actually naming Lagrangian fillings and L-compressible systems. A quick comment on the immersed part. A priori, I could have a tree. This is not happening here, but I could have a tree that starts somewhere, it branches out, and then kind of goes out in some way, and then it goes and intersects itself. That can happen. So the general machinery gives you trees, which sometimes might be immersed. And in fact, you can prove a posteriori that you couldn't have chosen them embedded. So this business about L-compressible systems, as I said before, in practice, in the papers and everything, you allow some of this to be immersed. And that, I mean, that is something you actually need to allow, because otherwise you're not going to find, say, maximal compressible systems for, say, Richardson braids or something like that. Okay, so explicit diagrammatic description of these L-compressible systems and Lagrangian fillings via these white trees. And both Dapping and Jose will elaborate on how to construct functions out of those trees. So now those trees will actually give you functions somewhere. And that is sort of part of the statement in these things being cluster A variables. So I'm going to conclude this geometric setting by just summarizing. So the first upshot is for this class of Legendrian weaves, of Legendrian links, the weaves gives you many Lagrangian fillings with L-compressible systems. All right, that's a good thing. Now, this is sort of purely geometric. I haven't used any categories. I haven't used absolutely anything. This is something that you can build by hand. You do it. Now, the next upshot, and that's what the rest of this talk and Dapping's talk and Jose's talk will be about, is now you try to compute invariants for the Legendrian links, say things about them. So for instance, you can take the category of sheaves, which I'll discuss momentarily, and you can think about the Lagrangian fillings that you've built through weaves. What kind of objects do they describe in this category? What are ohms between them? How do I compute anything with them? The advantage of weaves, and an upshot that it's really important about weaves, is not only you're doing the geometry explicitly and combinatorially, but all these computations in these categories also become rather explicit, not combinatorial, they become more algebraic geometry, but it's sort of classical algebraic geometry, quote unquote. It's about flags and transversality of flags and cohomology of flag varieties and things like that. So not too bad, given that, a priori, you know nothing about this DG category at an explicit level. Now, I should emphasize that because of this explicit computation, one can prove key steps such as regularity of cluster variables, a global regularity, which is going to be key, as I'm going to emphasize, and Jose and Dapping will also emphasize. In addition, because of the explicit nature of the computations, you actually get to prove more stuff. So for instance, you can, I'll discuss this in the second talk, you can show what is the Donaldson-Thomas transformation. You can show explicitly that these infinitely many candidates that you've built with weaves are actually distinct Hamiltonian isotopy classes because you show they're different objects in the category. And how do you do that? You compute exactly like what that object is, or at least you know enough about the object that you can tell them apart. So again, that explicitness actually is what translates into new results for the weaves. Okay, the last comment is that I'm not going to delve into many other interesting things that I think are interesting, at least, which is weaves do appear in other settings, and as we brought them up, as the paper was written and other experts talked to us or people attended our seminars, people started to say, oh, this looks very much like X or Y. This looks like the Elias-Kovanov calculus. Oh, okay, have you seen the Gayoro-Mornitsky spectral networks? It seems there might be a relation. And indeed there are, and we're working through some of them. We have finite time, but they do connect to other areas, particularly in geometric representation theory, particularly in combinatorics and commutative algebra, which I find interesting. But that's sort of not symplectic, and I kind of take this seminar to be maybe more centered on symplectic geometry. So I conclude here sort of the symplectic geometric discussion with regards to Lagrangian fillings and compressible systems, and I'm going to spend the last 10 minutes discussing algebraic invariants, microlocal invariants, categories, and the like. So I'm going to stop here for any questions sort of about the topology in geometry, and now we're going to shift into the categorical world. Yeah, any questions?
Roger, it's Renato.
Yeah, hi Renato.
Can you just tell what's the intersection between the boundary of the disks, I think gamma 4 and gamma 6, where one passed through the other in terms of the weaves?
Yeah, that one is 0.
Okay.
I mean, yeah, there's a general formula to compute these things, but yeah, this one is 0. Does that answer the question?
Yes.
Yeah. Okay, so Dee, yeah, I don't know if she's there, if they're there, but there's a question in the chat that says, are the exact Lagrangians built in this way, decomposable? And the answer is yes, they are decomposable. The D4 minus cobordism is a decomposable cobordism. You can actually break it down generically so that it is a pinch move, so a Lagrangian one handle being attached. And our 3 concordances are also decomposable because they're just Legendrian isotopies. So all of these guys are decomposable indeed. And again, to my knowledge, we don't have any provable non-decomposable Lagrangian filling in the 4-ball. Okay. Hopefully that answers the question. If you want more, just ask again in the chat. Okay, so there's another question in the chat. It says, how do we know those gamma I form a basis of HI? Yeah, that's a fair question. I mean, it depends on the situation and how you build the gamma I's. But for instance, let's go back to the example in here. So these gamma I's, like, how have you built them? Well, the way you've built them is by using the trivalent vertices. So a first geometric comment is that this surface, just as a smooth topological surface, and that's all I need right now for homology. This is actually a 3-to-1, in general is an n-to-1, depend if there's n plus 1, sorry, if there's n colors, it's an n plus 1 branch cover. So n plus 1, so n is the number of colors. It's an n-to-1 branch cover of whatever surface you're working in this case is the plane R2. And it's branched exactly at the trivalence. So this is a branch point, 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 this is a branch point. So there's a total of 8 branch points. It should work out, right? The Euler characteristic now, it's 3 times the Euler characteristic of the plane minus 8. It's minus 5, and minus 5 is indeed 1 minus 6. So things work out. So you know that you have the right number, but do you know they're linearly independent? And one way to go about it is you compute intersections. And in this case, and many others, just the intersection equivalent will tell you that they must be linearly independent because no guy has intersection with the others the same as other people. But there's also just a direct geometric argument for this kind of Demesur weave, which is because these are branch points, they generate the homology. So here, there's essentially just a bunch of disks. And as you go down, this generates homology or relative homology, if you wish. And each of these guys generate the homology. So now what's happening? This guy, gamma 1, intersects this point once, and no other cycle does. So in homology, this guy is different from anybody else. So you take this trivalent, gamma 3 intersects this guy once, and nobody else intersects this trivalent. So in homology, this gamma 3 class must be different from anybody else because the trivalents themselves generate the homology. So for this kind of Demesur weaves, just by looking at the branch cover structure, you deduce that these things must be linearly independent. Does that answer the question, Mingyuan? Well, otherwise, just again, write in the chat again. So now,
sure, thanks.
Yeah, great, thanks. So Nick, Yoon is asking, can you always find minimal generators of Y-tree that generate H1 of Lagrangian fillings? Well, I think that would go through the answer to the question, what is a minimal generator of a Y-tree? And the short answer to this is, I don't have a precise sort of definition of minimal generator, But if we made a definition, say, it's the minimal number of hexavalents, or within the tree, the minimum number of trivalents, something like that, I would tend to believe that those cycles built through the Lustig rules, so I haven't gone into detail of what that is, but there's a systematic way to build those cycles, and we call them Lustig cycles. If you use those Lustig cycles, then those guys should be minimal. Like minimal as a whole set. So let me, so Yoon's question is interesting also in that you could say, is this tree like the minimal tree representing the homology class gamma 2? Minimal saying that it has a trivalent, could I make it a short edge? And the answer is no, it's not. It's not minimal. Like I could do equivalences on the weaves so that this purple guy becomes a short edge, like this guy. So one by one, you could simplify one of them, but them as a whole, you could not. If the equivalence that makes this guy simple, like very short, it's going to make that guy very long. So there's sort of this trade-off. This was beautifully exploited by James Hughes, graduating student here at Davis, by in the case of D-type, by showing that in D-type, you can always mutate at any vertex you want. And the way you do it is the vertex might be a very complicated tree, but you can always simplify that one to be very simple. And maybe the others get very bad, but that's fine. In the next step in the mutation sequence, you're going to like simplify another one. So maybe that answers the question of Nick.
Thanks.
All right. Yeah, thanks, Nick. Okay, so let me just delve briefly now in 5 minutes into the DG categories and the like, which don't worry if it's fast. Dapping will start his talk reviewing how that goes. So the general setup is as follows. We start with our Legendrian. That's good. I'm going to skip over the fact that we're going to have a set of mark points. That's important for the decoration, but if you're not used to decorations, that's fine. And now you consider sheaves in R2 whose singular support is lambda. Lambda lives in the unique cotangent bundle. Makes sense to ask whether the singular support is contained in it or not. In particular, if you had a front for lambda, like an odd diagram, the sheaf must be constructible with respect to the stratification that the front gives as a stratification of R2. So that's your category. You're now going to draw sheaves in R2, which are constructible with respect to a front of lambda, and then there's some additional conditions imposed by the fact that the singular support must be contained in lambda. Exactly. Now, general statements, and I'm going to do an example in a second. General statements, Guillermo, Kashiwara, and Shapiro show that if you take this category, and in fact, compact objects in this category, that's a contact isotopy invariant. Beautifully enough, I recommend you read that paper. I think it's 2012 or 6. I think it's 2012 at Duke. The contact isotopy is actually not just arbitrary, but it's built through a kernel. Namely, it's a sort of pullback, push forward construction. So the way that you prove that these categories are equivalent is by building convolutions between them. So it's a very nice geometric construction. And the way OMs work in that category is just our OM of sheaves, which are just generalizing intersection of supports. The next quick comment is this category is well behaved enough. It's what's called finite type, which I can define if you want. But in that case, the moduli of objects that Tohen and Vacchia defined for DG categories, the full name is the moduli of pseudo-perfect objects, happens to be geometric in the sense that it is a derived stack, it's D- stack, but it actually is locally affine presentation, and it's also like locally geometric. So within the general sort of dramatic sort of what's the name? Sort of bad things that can happen to your spaces. These are particularly nice spaces. Okay, so let's just go down to earth. So when lambda is of the form lambda beta, these guys are actually affine varieties, and they can be presented in this way. And this presentation is the one that Jose and Dapping are going to use. So what you do is you take the front here, you describe the stock of the sheaf in each strata. So for instance, the stock here is just C, the stock here is C squared, C. Here, I'm drawing a particular kind of moduli, those which have microlocal rank 1, and I'm going to implicitly assume that I'm always imposing microlocal rank 1. And then you have the data of maps, which is the parallel transport between those stocks. The maps truly go from this stalk to the stalk in this part of the strata, and then from this part of the strata to the next strata. But actually, strata which are not top dimensional always have one direction being an isomorphism. So all you need at the end is describing maps between top dimensional strata. So the upshot here is, at the end of the day, if you have one of these lambda beta, the model I of sheaves looks as follows. You choose a bunch of vector spaces according to the number of strands you have. So if you have 2 strands, it's 0, c, and c squared. If you had 3 strands, it would be 0, c, c squared, and c cubed, so on and so forth. And then maps. So that's a map from c to c squared, another map, another map, another map, and then this other map. And the construction of singular support tells you, and that's a condition that was studied by Shende, Truman, Zaslow in 2016, if you want the singular support to exactly be the Legendrian and not include any other directions, these 2 maps on the right and on the left of the crossing must be transverse. So the upshot is, at the end of the day, this model I is just 5 vectors in C2, this one from here, one from here, one from here, one from here, and one from here, the kernel of this map, such that they're transverse to each other. And in fact, you can actually impose that the determinant is 1, and then you got them out by the SL2C symmetry overall for this central fiber. You can write equations for that in general. Jose will explain in detail how to write some equations. But in this example, for instance, you get this nice smooth affine variety. All right, so I'll skim very fast along the next slides, but the punchline that I want to tell you with regard to these spaces is, from this Legendrian knot, you get this model I of objects. Now, what this really does is it's trying to incarnate, it's trying to provide you with some nice space, a smooth affine variety in our case, that parameterizes Lagrangian fillings. So you can read the slides slower afterwards, but what's important is, if you have a Lagrangian filling, then if you endow it with a local system, you get a point in that space. So more generally, if you're just thinking about a billion local systems, well, GL1C local systems, then a Lagrangian filling will give you a toric chart inside of that space. Now, how do you compute that toric chart? Well, if L comes from weaves, that can be computed explicitly. And Jose will explain that in detail. I think dapping in part 2. So you can distinguish those Lagrangian fillings via these toric charts. The second comment is, as I said before, if you happen to have an L compressible cycle, so one cycle that bounces Lagrangian filling, you can perform this Lagrangian surgery, get a new guy, you get a new toric chart. But furthermore, and that's going to be in dapping stock and in Jose's, this cycle in the Lagrangian filling actually gives you a regular function. How to define a regular function? Well, that's going to be in dapping stock. There's called microlocal merodromies. And what's really interesting about that function is that despite the fact that it's defined only as a regular function on the chart given by the Lagrangian filling, it extends to a regular function on the whole space. So again, here what you're seeing is something non-trivial, in that you have this specific Lagrangian filling in mind. It gives you this specific toric chart in your space, and you define a specific function which a priori is only defined in that toric chart, because it really uses that Lagrangian filling. And the claim is there's a way to extend that to a global function on the whole space. So for instance, you can go and evaluate that function in a chart which is like far away from your Lagrangian filling. Maybe it has to do with some other Lagrangian filling which is really far from yours. And yet the function can be evaluated there. You can get meaningful numbers. It doesn't have poles. It's a regular function. So the extension is proven via weaves. And in general, this set of coordinates actually do change under Lagrangian surgery according to cluster mutations. Okay, this is an example. I'm going to skip the example. You're welcome to read the slides. I want to finish somewhat on time. So the example here would just explain how you would think of those flags. That's in the model I. And then every time you have a weave, you impose additional transversality conditions between the flags. All right, just skipping this quickly. The main theorem that Dapping and Jose will explain to you is, if you take that modelized space that I just introduced, then all the weave and all the L compressible system construction, all that geometry allows you to prove that the regular functions in that space is a cluster algebra. What is a cluster algebra? Yeah, Dapping will explain that in more detail. Jose will explain that in more detail. But the point is, you've found a symplectic geometric construction that actually allows you to do a lot of things in cluster algebra that were not like doable before, because computations were not explicit enough, because there was no global description of what a cluster algebra is typically. So I'll let you read the slides yourself. This model space parameterizes Lagrangian fillings. It will have a meaning at the level of geometry, what it means to be cluster. And finally, I will explain in the second talk what are some useful applications of having this cluster algebra. And it solves a series of problems that I would otherwise not know how to address without cluster algebras. All right, these are some comments that I will go in the next talk. And I just want to finish by saying two things. The first one is we had an AIM workshop in January that was rather fruitful, and a lot of projects started there in relation to these. And there's going to be an Overwolfach Arbeitsgemeinschaft in October 23 that if you were interested, you could apply for. That's organized with Bernard Keller and Lauren Williams. So there's some other occasions apart from today in which these matters will be discussed in detail. And the second and last thing is I really want to bring up some of the names of people that have done work in this area before me and in which those results are actually built on. So Kashiwara, Shapiro, and Guillermo are three important names. Then there's a lot of work done by David Nadler and then Eric Zaslow and his collaborators as well that developed the theory of sheaves and allowed to have structural results. And then more recently, with regards to the cluster algebra, Honghao Gao, Lin Hui Shen, and Daping Wang, along with Ann Ba, Hugh-Jin Lee. And finally, my more recent collaborators, the Gorskys, Eugene and Misha Gorsky, Jose Cimental, Ian Lay, and Lenny Inc. And some of the work also builds on some ideas of Thomas Kalman. I should maybe just say that, as I said, this connects to other areas, and the work in these other areas have connections to those names. So if you want to learn about spectral networks, you want to learn about like the circle calculus, Elias and Kovanov are the people to talk to. You want to learn about cluster algebras or cohomology of positroids, Galatian, Lam, Spire, and company are good people to talk to. So just to put it out there, obviously there's a lot of work before us, and I just wanted to honor that properly. All right, this is the biography. Now Daping will talk in a bit, and I'll talk later. Thanks a lot. We conclude the first talk here.
Thank you, Roger. Let's thank Roger, and I'm going to do it by. I'm going to open the floor for questions, but before that, there was one question that that was in the chat that we kind of missed. It was by Dee Reisinger, and she asked if the exact Lagrangians that you build through these weaves are decomposable.
I believe I answered that during the talk.
Okay, sorry, then I must have missed it.
I can answer again briefly. The answer is yes, they are decomposable. Maybe video of the recording will provide more.
Will provide evidence. Yeah. Okay, any other questions? Can I ask you, so this function that you say gets produced in every chart and then becomes a regular function, you know, in Lagrangian Floer theory, we can produce functions as disk counts. Does it have such an interpretation?
Not that I know of. It's more to do, so I can describe it a bit, and maybe you can say if that has to do with disk counts. It's more to do with counting disks and then keeping track. So these are not disks now, they're relative homology classes because they're strips with a puncture on the rep cord. So you keep track of like of these guys, and then because you have a local system, you compute the monodromy around that. Now, I think in the closed setting, the monodromy would be just a curve, an absolute cycle, and that you could keep track of that H1 class and put the monodromy there. In this relative setting, you only have this relative cycle in there, and you need this decoration. And that's key, because the way you compute the analog of the monodromy is you parallel transport the decoration from one point of the relative cycle to the other point of the relative cycle, and then you compare, then you take the ratio of that. So in fact, you can actually compute monodromies around the absolute cycles, the gamma i's that I said. The bad thing is you do that, you get a rational function, honestly, with poles. So the way to sort of go about it is to take a Poincare dual basis of these gamma i's to relative cycles, and then really use these decorations that you have in the lambda to then compare decorations, and then you get regular functions. So the short version is it has something to do with counting holomorphic disks, but the thing that I don't know symplectically, and maybe you or Denis or somebody has insight on that, is how do you name these special cycles inside of H1? Like what these L-compressible systems are doing for you, the way I've built them is they're able to name some cycles that when you apply this construction, it works. You get a regular function. But if I went for some other cycle, if I took like some weird cycle in there, and you do the same thing, you can check, I've checked, like you don't get a regular function. So there's something special about those cycles that bound embedded Lagrangian fillings on the complement. They are such that when you then count disks and do holonomies, those guys are regular. But I don't know how to name the first thing sort of symplectically.
I think I understand something. I have follow-up questions, but maybe not for right now. Anybody else have any questions? Okay, I'm going to pause the recording. I will not leave the room. We will resume in 5 minutes with Daping Wang's talk. Yep, thanks again.